I suggest, so I welcome back everyone to the second session of our Machine Learning in OCT Imaging Symposium. My name is Martin Villiger. I'm assistant professor at Harvard Medical School and part of CBORT here, where I'm leading research in advancing catheter and probe-based OCT imaging. The second session focuses more directly now on OCT and machine learning in OCT. We will start off with an overview of the basic principles of OCT, followed by a talk illuminating more of the pathologist's perspective. And then the session concludes with a specific case example of AI-powered OCT imaging, which is pursued in an industrial setting. I'd also like to quickly remind the audience here, so we are recording these, or most of these talks, and they will be available later for download from a site that we communicate with all attendees. So for the first talk, it is my pleasure to introduce my colleague, Nestor Uribe-Patarroyo. Nestor is a physicist by training, currently an instructor at Harvard Medical School, and also part here of CBORT. Nestor has been applying his physical mind to the intricacies of OCT imaging and will share here some of his insights with the motivation really of giving someone with a kind of more machine learning or general medical imaging background a shortcut to a deeper understanding of OCT. So please, Nestor.
Thank you, Martin. I will start just with mentioning briefly. I will start with a little bit of the basics of OCT imaging. Then I will go into some current challenges in structural OCT imaging, and we'll finalize with a brief introduction and open opportunities for machine learning in functional OCT imaging. So OCT is a cross-sectional imaging modality that uses mostly infrared light and has been traditionally described as an optical analog of ultrasound imaging. And it works by detecting reflected light or scattered light more rigorously from a volumetric biological sample as a function of depth. I will explain exactly what depth means in this context a little bit later. And then it's essentially composed. So I will just get my pointer. It's essentially composed of a light source with a detector and then an interferometer that allows us to send light into the sample using focusing optics. And then we detect the light that is scattered by this sample, and it's coupled back into the system. And it's mixed with light that is sent into a reference mirror and coupled back. There are essentially two options for implementation of this. We can use a white light source with a spectrometer. In this case, we will have a spectral domain OCT system that generally can achieve higher depth resolutions, but have moderate A-line rates or imaging speeds. And in the case of using a wavelength swept source coupled with a detector, we're talking about Fourier domain or wavelength swept source OCT that can achieve higher speeds. And OCT sits nicely in between ultrasound and confocal microscopy in terms of the trade-off between spatial resolution and penetration depth that we can achieve. So depth is in reality optical path length, because we're measuring it with an interferometer. And what we do is that we encode this optical path length into the frequency of the signal that we acquire. This signal is what we call a fringe. And depth profile, what we call an A-line. So we can see, for example, that at the top of this sample, we have, for example, the signal that comes from the superficial layer will be encoded into this low frequency sinusoid, and a deeper layer will be encoded into this higher frequency sinusoid. So essentially what we do is calculate a Fourier transform of the fringe that we acquire in order to reconstruct a depth profile of the magnitude of the reflectivity of the sample that I'm displaying here very narrowly. And then most systems are provided with scanning mechanisms to displace the beam laterally across the sample so that we can create two-dimensional images called B-scans or three-dimensional images. And in this case, for example, I'm showing what a B-scan of esophageal tissue would look like, in which we can appreciate very clearly the different layers that we have here. Now, I want to clarify that the depth resolution in OCT is given by the wavelength spectrum of the source that we're using, but the lateral resolution is given by the focusing optics that we're using. And in a typical benchtop system like this one that is generally used to image, for example, excised tissue, skin, or small animals in preclinical studies. We have typical depth resolutions of 4 to 7 microns and lateral resolutions of around 10 to 30 microns. When we are imaging the eye, that is one of the, well, definitely the most widespread application of OCT, we replace the focusing lens by actually the eye. The eye performs the job of focusing the light. And the scanning mechanism pivots the beam at the pupil in order to create this scan pattern on the surface of the retina, and so that we can create these cross-sectional views of the retina in which we can appreciate the layer of the retina, or emphasis projections in which we can see for example, in this case, we're close to the top layer of the retina where we can see these blood vessels. In this case, the resolution is roughly the same, typically. In the case of lateral resolution, when there are no adaptive optics used, in the case of clinical systems, for example, the resolutions are roughly 15 to 20 microns. And more interestingly, we can also couple an OCT system with an endoscopic interface in order to essentially have coupling of the light that we have in the sample arm between a static fiber that is connected to the interferometer and a rotating fiber that is connected to an endoscope. So this allows us to scan luminal organs with an endoscope from the inside of the organ, and we can have 2- and 3-dimensional scanning by azimuthal rotation and also by pulling back motion. So this is an example of esophageal imaging using OCT, and it's just to give an idea of the magnitudes that we're talking about. So we can see the scale bar. This is the esophagus is a pretty large organ. So this is using a balloon catheter, and the actual diameter between this and this end of this surface of the esophagus is roughly 20 millimeters. So this means that a single B-scan in this case is acquiring roughly a field of view of 60 millimeters in the esophagus. For these reasons, also lateral resolution is usually a bit lower in the endoscopic systems, in the order of 20 to 60 microns. Now, the imaging geometry of OCT defines many of its properties. So first of all, the magnitude of the signal is not an intrinsic property of the tissue, because it combines information from the light attenuation that happens at superficial layers and the scattering strength that is intrinsic to this particular tissue type. So we can see that as light starts to penetrate into the tissue, it starts to get depleted because of interaction with the tissue via scattering and absorption. Essentially, the amount of light that reaches different depths becomes to decrease exponentially. So that means that the light that reaches the deeper regions that we're able to image is order of magnitude lower than the light that reach the top layers. So that makes up, we need to adjust the way in which we interpret these images to take this into account. So for example, we can see that here the epithelium and the submucosa have roughly the same magnitude visually in this image. However, because the epithelium is very superficial and the submucosa is really deep into the tissue, we know that the actual scattering strength of each one of these layers is going to be totally different. The submucosa has to be much stronger in the contrast. So if we were able to create this, let's say, more absolute intrinsic image about what is the scattering strength of the tissue, it would actually look like something like this. However, we have a combination of factors governing the light attenuation and the scattering contrast. So we cannot, from a single OCT image, we cannot actually determine the true local tissue scattering properties. It's an ill-posed problem. We don't have enough information for this. This is actually a very interesting problem. It's an active investigation, because scattering properties of tissue carry information on tissue microstructure, which is known to change in certain pathologies. These are two examples of leveraging from this type of analysis. in order to obtain microstructural information on tissue, in which the bottom one is actually from our group that is currently under review. However, as far as I know, there haven't been any attempts at leveraging from machine learning in order to crack this problem. Now, I would switch gears to speckle. This is a big topic in OCT. So the fact that we're encoding depth in fringe frequency requires the use of coherent radiation. And using coherent radiation implies OCT is a coherent imaging technique, which gives rise to speckle. So to visually explain what a speckle looks like, I just created this simulation in which I used this piece of histology. And for the pathologists in the audience, I know this is not esophagus, but I just used this intestine H&E stain histology to create manually this ground truth for what esophageal tissue would look like in terms of a scattering contrast in OCT. And then if we use the known physics of OCT, the B-scan of this ground truth would look like this image that we have on the right. So for this one, I chose a typical endoscopic resolution. Actually, the block dot here is the PSF of the system. So what we can see is that definitely there's this pervasive grainy pattern in the image. This is speckle. And I want to clarify that this is just 1/60th of this whole scan. So this relatively low resolution that we see visually is just because we're looking at a really, really small region of interest right now. So the problem with speckle is that speckle has unity contrast. So it really, really affects in a fundamental way our interpretation of the image. And also the average size of the speckle is exactly the diffraction limited resolution of the system. So this means that interpretation of the structures in the tissue that are at the scale of the resolution are the most affected by it. If we had a magical way to create an incoherent version of this, which is what we would see in MRI, for example, we would actually have image that looks like this, that now we can really draw a much closer comparison between the ground truth and this incoherent image. We can actually see at these higher intensity inclusions that this could be, for example, glands of interest in a certain pathology. But in this case, especially when we look at, for example, these red ROIs that I have here, this inclusion was actually evident in this low-pass filter version in coherent imaging. But in the case of OCT, it was indistinguishable from speckle. So we cannot tell really if this small structure here is just a bright structure in the tissue, is a bright speckle. So this is why speckle is such an important effect in OCT that we have to consider. So if we had a way to shake the scatterers around in the tissue to essentially change the microscopic organization, we would create different speckle patterns. And this is exactly what I'm showing here on the right. So I hope that you can see this. So this is essentially all of these speckle realizations are completely compatible with exactly this incoherent image. So a single incoherent image can be associated with an infinite amount of speckle patterns. If we are able to, in practice, implement this type of organization of the scatterers, and we actually perform an averaging of all of these images, we would end up with an OCT average that is exactly this incoherent image that we will have on the left. And in this case, we can recover the actual true underlying structure that we were seeing in incoherent imaging, and we can actually identify this gland as a bright spot. And so this averaging is the basis for most speckle reduction algorithms. And this visualization makes it clear why this speckling is such an important topic in OCT structural imaging post-processing. So there have been ongoing attempts at deep learning the speckling. But really the main challenge is obtaining proper training data. And I want to emphasize that most of the works that have been published use either out-of-plane averaging or B-scan compounding. And these are not appropriate strategies for different generation of training data if we want to preserve the spatial resolution of the despeckling process. So if we want to acquire proper training data, we need to have non-standard hardware. So we're only aware of this single publication in which they actually use training data that aims at preserving the spatial resolution of the process. So, but even in this case, I'd still say that I think that convincing the speckling using deep learning remains to be accomplished, and it's definitely a big opportunity for advanced machine learning architectures. I also want to mention a little bit about single and multiple scattering in OCT. So the image reconstruction in OCT assumes that this optical path length directly equates to physical depth, and that this is how we show the images. But this assumes that we're in a single scattering regime. In OCT, we only have partial rejection of multiple scatter light. So this means that it's light that bounces inside the tissue multiple times and is eventually captured back by our system. So it looks like it's coming from a certain depth, but it actually carries information from different locations of the sample. So this creates distortion and blurring in OCT. So far, really the only way to get some insights into multiple scattering and the content of multiple scattering in OCT imaging has been to create custom hardware implementation. So in our group, Vicente Paró presented this work at Photonics West this year. He essentially created an OCT system with different illumination detection paths, similar to speed detection and confocal microscopy. And he was able to roughly get an idea of this is porcine retina, excised porcine retina. This is an MFAS view. And he was able to estimate the amount of single scattering and multiple scattering contributions that go into this single conventional OCT image. And I think that we can really see when we look at the single scattering content, we see that there's actually quite sharp contrast where the retinal nerve fiber layer in this case. So we see these radial structures are axonal bundles. We can see them much more clear in this single scattering image. And now we can actually start to see that the conventional OCT image had a kind of a haze that was actually produced by multiple scattering. Even at this layer, there is actually the most superficial layer that was imaged in this case. So definitely separately, single scattering, multiple scattering in conventional OCT systems would be huge also to improve the interpretability of OCT image. But also it's useful for diagnosis because the degree of multiple scattering can provide information on microstructural parameters. So it's actually not only for improving the visualization of the data, but also to provide us with some information on the microstructural information that we can actually see in the image itself. There are other opportunities for machine learning structural imaging. So first of all, I want to emphasize that because of the way in which the optics and wavelength scanning works in OCT, that they act as low-pass filters, really there's no physical basis for super resolution when we have the dense sample with speckle. So instead of focusing on super resolution, I would say that super sampling, for example, is an attractive alternative to this goal. This is essentially trying to reproduce Nyquist sample tomograms from tomograms that have been scanned much faster, because there are some advanced post-processing algorithms that require Nyquist sample tomograms, such as computational adaptive optics. So if we can scan faster, that means that we can avoid patient motion artifacts. And for example, in the case of the retina, it will be really useful to be able to scan much faster, but then still be able to perform computational refocusing to be able to see small details in the retina, such as photoreceptors. So I will leave the details about this to the breakout session. I will just mention another opportunity that is the case of reconstruction of tomography in extended wavelength swept sources. So in infrared domain, we're limited in terms of the bandwidth that we can achieve because there are limited availability of gain media for these types of lasers. So there are some islands of appropriate wavelength ranges that we can use. So we could envision, for example, if we could use some of these ranges that are far apart and have a big gap in the data. So similar to the MRI case of sparsity sampling, but in this case, it's not really sparse. It's about having blocks and then having big voids in between. Would it be possible to have a reconstruction of this in which machine learning would essentially try to avoid the artifacts, these really strong artifacts that appear that we have here in the case of B, when we have these kind of gaps in the spectrum. So in this paper, they use a technique that was developed for the radio astronomy. The problem is that radio astronomy doesn't have speckle. So it works for point scatterers like this image, but it doesn't really work for dense samples that are of interest. So I will now switch gears to functional imaging. In this particular case, polarization sensitive OCT. So there are many tissues that exhibit fibular architecture, and they exhibit what is called birefringence with a given orientation. Essentially, this is about the orientation and the type of fibers that are components of the tissue. And PSOCT determines the change in the polarization state of the light as a function of that allows us to determine what is this if there's birefringence presence in the tissue and what is its orientation. And also, when fibers are not perfectly aligned, this can give rise to depolarization effects. So there's high potential for PSOCT in clinical applications such as intravascular imaging, and because the work that Martin Villiger has been leading, or in retinal imaging to be sensitive to axonal degeneration in glaucoma, for example. So in Martin's work that I'm showing here a figure from reference 1, for example, he has found that there's actually a very close correlation between some parameters that are determined in PSOCT, such as, for example, the birefringence, and the collagen content that is determined in histology using specific stains. And for example, the depolarization that happens in lipid pools in plaques, that are really important for informing the process for the intervention in these patients. So now, other opportunities for machine learning and PSOCT will be, for example, to enable quantitative interpretation of these parametric parameters that we get in tissue. So at this point, I think it's more qualitative in the sense that we can draw conclusions on whether there's presence of birefringence, it's high or low birefringence, but we don't really are able to get anything about, like, can we get any metrics about density, collagen type? There are the metrics that we can actually get from histology. So it would be really interesting to see if it's possible to uncover a complicated relationship that exists between intensity image, these parametric parameters, and then what we can, the conclusions that we can draw from histology in terms of the actual organization of this, the fibril architecture in the tissue. However, of course, this requires this complicated creation of training data, labeling using other modalities, and this is definitely a challenge because we require matching histology, which is definitely not easy. And then to end, to briefly mention OCT-A, so angiography aims at visualizing blood flow in tissue, and it relies on temporal evolution of the speckle patterns. So we have an example here in which speckle moving implies that red blood cells are moving in tissue, and then what the speckle is this is static. That means that this is essentially not perfused tissue. And then we acquire repeated B scans, and then we perform the correlation analysis to get information about blood flow. This has been used in, for example, preclinical studies of tumor biology, and has been found huge, really potential applications in ophthalmology. So this is an example of its use in glaucoma or in diabetic retinopathy. And there actually there has been a recent publication from last year in which they were trying to tackle a big problem of OCT. The fact that we have to acquire repeated B scans means that there's increased acquisition time, and which is an obstacle for adoption. And they were trying to see if training a neural network with 48 B scan repetitions, they were able to essentially get only 4 repetitions to provide the same type of quality that 48 repetitions provides. And so far, the data actually looks pretty good. However, this is not retinal vasculature. That there will be challenges there to acquire the ground truth data. I will leave this other opportunity for the breakout session, and I will just conclude saying that, well, OCT imaging has many quirks, and they're not present in other imaging modalities that have seen these much wider developments in machine learning. There are definitely many open opportunities beyond segmentation and classification, and we hope that it could actually help us bring advanced functional imaging to the masses. So I just want to conclude acknowledging all my colleagues in the lab, and thank you for your attention.
Thank you, Nestor. It's a very insightful talk. I particularly liked your speckle simulation based on histology slides. That's a very nice demonstration. And maybe a perfect segue here into one of the questions. What do you think of using simulated data to train machine learning for despeckling?
Yeah, so it's possible. I think that as an initial attempt, it could be interesting to see essentially what is possible, because there is still this big question about, like, we saw that the single incoherent image is compatible with an infinite amount of speckle realizations. So can we actually go from any of these one to recover this unique incoherent image? I think that is a question that can be answered with simulations. But I think that if we want to actually bring this into more realistic imaging, simulations are not great to capture many of these complicated issues in OCT, such as multiple scattering, for example. So I think that in that case, it probably be a good as a test bed, but not as the actual way to develop this.
Yeah, I think I kind of share your view, but it would be interesting actually to hear some, like, Florian's opinion on this, where it seems that in MRI, indeed, you can get quite far with generating synthetic data, but with these additional quirks of the OCT signal, indeed, that may be more challenging. Maybe one other question here, kind of principle, to elaborate more on the basic properties of speckle. What did you mean by unity contrast of speckle?
Oh, yeah. So essentially, if you had a given incoherent structure with some intensity, so the speckle will be modulating the value of that structure from 0 to its value. So the modulation speckle covers the entire dynamic range of your signal. So it's not like additive noise in which you will have some modulation on top of your signal. It will actually modulate completely. It's usually explained as multiplicative noise because of that property.
And well, maybe also, right, we've displayed the tomograms in the logarithmic scale, though, which can cause confusion in it. So I guess the unitary contrast is in linear scale.
Absolutely, yeah.
There was another question here related to PS. If PSOCD has been considered a possible resource to compare speckle resolved training data sets. So I'm not sure if you want to comment on that. Or if they,
I'm
not sure I exactly understand the question.
That's related to the potential speckle modulation that you can get from varying the precision state that you're using to illuminate the sample. The problem with that is that you're essentially limited to two different uncorrelated speckle patterns, because the basis for precision states is it has just two states. So really, we wouldn't be able to get great speckle reduction by just averaging two images.
And now this two kind of related questions. We're running over time now, but maybe you can briefly comment on, would it make more sense basically to use the raw data to deal with speckle suppression, or starting with the already reconstructed image?
Yeah, so I find that difficult. I will have to think more about it. But the thing is that really the Fourier transform relationship between fringe and image exists when we have a coherent image, a coherent, and I mean it's a coherent system. This is what allows us to do this, because we encode this coherent radiation distance in fringe frequency. So actually, if we have reconstructed tomograms, when we average them to reduce the speckle, we actually lose the phase information. We cannot go back to the fringes. So these are fundamentally two different domains. The moment in which we start working on reducing the speckle contrast and suppressing the speckle, we're no longer in this duality between K space with fringes and image space in Z. So that's why I don't see a way in which that could be useful, but definitely, I mean, like, I think it's worth thinking a little bit more about it.
All right. So I think I would like now to invite the next speakers to request access to share their video and audio, and thank Nestor again for this insightful presentation. All right. So while Vladimir sets up here, I start introducing the last talk, which will be given by Vladimir Pekar, who's apparently struggling to get access. Okay, hopefully it works this time around. So Vladimir Pekar, who is the AI lead at Perimeter Medical, a Toronto-based company. Vladimir holds a PhD from the University of Hamburg and has an accomplished career in computer science applied to medical imaging. Vladimir hopefully will present the specific medical challenge that Perimeter Medical is addressing by using AI to make practical use of the large volumetric data sets that contemporary OCT can readily generate. So, yes, so we do see your slides. So please, Vladimir.
Okay. Yeah, thank you, and sorry for this technical problem. Yeah, thank you very much for the invitation. It's actually my first time of giving a presentation, since quite a bit, and definitely my first time at a virtual conference, and I hope no more technical issues. So today's presentation is about computer-aided detection of suspicious tissue in wide field OCT of the breast using convolutional neural networks. And Perimeter's device, OCT device, is an FDA-cleared system for general indication. It's not really specific for breast, but in this presentation, the clinical application is breast, and the AI algorithm described has not been cleared yet and is not available for sale. It's a research prototype. Repeat surgery after lumpectomy remains an issue where about 25% of all women have lumpectomy, so they have to return for a second surgery. And a recent study, so in patients with IDC and DCIS, so the positive margin rate was 25%. So basically it means that 25% of patients didn't have clear margins and have to eventually come back for a second surgery.
Vladimir, just to point out, I'm not sure, we are still seeing your first slide in just the slide, regular slide mode, not
Really?
in presenter mode.
So what I'm doing, I'm just trying to scroll.
No, it's not scrolling. So I think now it did move to slide 3. We now do see slide 2.
I just doing this.
Very good. Yes, that suggests just.
Yeah, can you read it? Okay. Yeah. So let's go back to this slide. Yeah, as I said, so 25% eventually, 25% of patients eventually have to come back for a second surgery. And OCT imaging is quite effective at visualizing tissue structures, as you can see here, where we can see correlation of features between OCT required during surgery and standard of care histopathology, yeah, which is typically available later. So so you can see there is a visible correlation of different tissues. So current standard of care is, of course, histopathology, which is available only after a couple of days post-procedure. And so what we would like to achieve is intra-procedural tissue visualization, where OCT is a very promising modality, of course, because it does not have any ionizing radiation. It's fast and it's very high res. So so that's where it becomes a very promising modality for this particular clinical application. And so perimeter system is a mobile system. So it's a cart which you can roll into the OR. So there's a touch screen for review and interaction. And here you see the imaging window. You can place excised specimen for imaging, and you typically acquire 6 margins, and you can assess the results to see if the margins are clean. So the reader or the surgeon can assess the margins intraoperatively. So here you can see comparison with ultrasound, which is also a mobile device, but OCT, of course, offers up to 10 times better resolution and up to 2 millimeter imaging depth, which is clinically relevant for surgical excision. So then, why we need AI to process data? So in our particular application, we have several hundred slices to review per case. And another additional challenge is that there is a wide field of view. It means that our visual system is not very well tuned to cover the whole field of view. So the user typically would look at one part of the image and then scroll and then look at the other part. So because it's impossible to cover the whole field of view. And of course, next comes that image interpretation is very challenging in the way. So if you can see at all these thumbnails, these ROIs are all suspicious. It means that there is no unique characteristics which ROI is suspicious. It means so typically in computer vision, where we can reliably identify structures, it's the case when they possess some unique characteristic, either in the appearance, like texture or shape. But here we have a huge variety of possible suspicious ROIs. That represents quite a big challenge. And so why neural networks is the way to go here? Because when I first looked at these images, I thought, wow, it's so difficult, because typically, in a long time ago, maybe not quite long time ago, you would approach this problem by designing certain filters or feature extractors, so that would highlight this feature in the image, and then you would be able to detect them. But in this particular case, there's such huge variety that makes the problem very challenging. But so luckily, neural networks are capable of learning all required filters simultaneously and automatically just by analyzing examples, as we saw today also in several previous presentations. And also, since time is very critical in this particular application, so GPUs also allow us to process images very quickly. Talking about the general processing workflow, what we suggest to do is, so we take extracted image patches, what we call patches, and pass them through convolutional neural network. And at the end, we have a separation between suspicious and not suspicious class. So the particular details of that, because several architectures can deliver similar results. So we tried several, and but what's important is if we feed many samples of suspicious and non-suspicious patches, the network is capable of achieving 100% accuracy on the test set. So if you train it long enough and then pass the same test set as test set, the network is very precise. So how we generate training data? So we have a wide field OCT, and we basically pass like a window through it and extract patches. And so we have labels that mark suspicious areas, and so we know which patches are suspicious. And since labeling is a very tedious process, so we will always have way less suspicious patches. In this case, we use data augmentation. So we flip the patches horizontally. We use shifted versions of the patches. In this way, we can augment the positive or suspicious test set. Oh, sorry, training set. So here's some results of model generation and testing. So we had over 100,000 ROIs to train the model. So we have our validation set. And so we use PyTorch, which is an open source environment, to generate the model. So it's all done in Python, and then we export the model using Torch script, and so we can use it in our product environment, which is C++, which is very handy. So it's a highly efficient approach. And so we tested the model on a test set of over 200,000 suspicious, non-suspicious ROIs, and achieved the accuracy, so the area under the curve of 0.94. And here's an example how it looks like in our prototype, so user interface. So here you have wide field OCT and with an unpassed image below, so the photograph of the specimen. And so the algorithm processes the 3D volume or the stack of B scans and highlights the suspicious areas. So then the user can click on there's a button, and it just quickly gives you an overview of all suspicious areas found in the volume, in the stack. So the numbers here in every square they are just because we group the detections together in the through plane direction, because we assume that a lesion is not only present in a single B scan. So then the user can highlight just like a patch which appears suspicious and where the user would like to have a closer look. And so you can go back to the place in the B scan stack and just scroll back and forth just to confirm that's indeed a suspicious area. So we did a quantitative evaluation on a test set of 155 margins, full margins. So we had 31 positive margins in the test set. So what's important is that we have 29 margins identified with true positive clusters, and 20 out of them where the thumbnail presented to the user was indeed a true positive. And on the full test set, the patch-wise sensitivity was about 70% and specificity 95%, and the user had an average around 90 clusters per margin to review. So it's indeed quite a bit, but we hope to, as we are able to feed more data to the algorithm, just to reduce the number of false positives in this way. So I was hoping to present results of clinical assessment, but the results are still underway, so under processing, and we had a reader study underway, which where clinicians evaluated a test set of 40 margins just to, and were able to identify the majority of them correctly within a couple of minutes, just 2 to 3 minutes, which is a really promising result, we think. And as a summary, so we have developed an AI algorithm using convolutional neural networks that have shown high confidence in classifying suspicious with no suspicious regions in wide field OCT. We have a research prototype of the device with a specialized UI that has been developed to allow for efficient data review. And unfortunately, the results are not there yet, but we have a multi-reader, multi-case study underway to assess clinician efficacy. So ImageAssist is our algorithm, and the whole project was made possible by a grant from the government of Texas, so-called CBORT. And I think we're back on track, and so we can have time for questions. So maybe, at least for the break session, I should be able to join the video, but maybe for the sake of time, we can just proceed with questions now.
Yeah, let's. Yeah, I heard that there's some echo happening. Can you mute yourself, Vladimir, while I'm talking? Thank you. I think that will reduce that echo. Perfect. So thank you for sharing the progress on parameter side. And to the audience, please don't hesitate to ask questions, a few questions through the Q&A chat. And maybe to start, you may have mentioned, but I missed. So, I mean, you explained that you know which patches are suspicious, but so this is again relying, I imagine, on an expert annotated ground truth.
Yeah, that's fully correct. So the expert annotated ground truth, but full segmentation was not needed. It just was a label placed on a scan. So then the patch was extracted around this label.
See, related to that, so you just have a label in the lateral direction. It's a certain area of the scan. So, but your patches seemed also to translate kind of in depth. So I was wondering, since you at least alluded that this is also convolutional architecture, isn't there a fundamental issue with OCT images, at least in cross, not being that invariant, because the images obviously look very different, deeper inside the tissue, and at one point fade out? Can you comment on that?
So yes, I think, I mean, first of all, the whole process is two-dimensional, right? Because we extract patches from B scans, right? And the clinically relevant depth is 2 millimeters, and this is where OCT still offers, enough, feature information to be able to proceed. And so surgically relevant margin is also about 2 millimeters. So I think if the margin is clean within 2 millimeters, then it's a good indication that it's clean and no second surgery is needed. So this is where I think the approach is viable.
Okay, so you're saying you're basically simply limiting the depth that you analyze is kind of 2 millimeters, and within that
Yeah,
area,
that's correct. So the patches, yeah, only
maybe
extracted from the top, yes.
So now maybe a question here from the audience. Can you go over what is needed for an AI algorithm to get cleared by the FDA in a diagnostic product?
Yes, it's a very good question. So I think it depends on the analysis done by FDA. For example, you can use 510K pass, which is a predicate device. So if your device is close enough to a predicate device, and so you can, get this cleared. Otherwise, the approach would be to run a clinical trial, basically, and just prove your so you're delivering what according to the expectations. I don't know if it answers the question, but it's a complex process. I believe the FDA has taken measures to speed up this process, but it's still the time frame can be quite substantial for that.
All right, I would suggest now, Vladimir, maybe that we switch over now into the breakout session and give you a chance to maybe connect, either reboot your computer or connect from a different computer into the breakout session as well. So with this kind of review, conclude the official second session here and thank all the presenters again, and reconvene in the breakout session that now should be available, where hopefully all the speakers can join us and we can field additional questions. And then the main event will continue at 1 p.m. with the third session continuing in the main program.